Assalamu alaikum. Bismillah. I'm going now to explain two sections, section 3 and 4. Section 3 talks about the hydrogen ions and pH. In this lesson, I'm going to talk about pH and pOH. And then we will relate both pH and pOH with their K and Kb, or concentration of H positive and the concentration of OH negative ions. All this is going to be about calculations. So the main idea of this section to talk about the pH and pOH are logarithmic scales that express concentrations of hydrogen ions and hydroxide ions in aqueous solutions. In addition to all this, we have lesson 4 or section 4 that talks about neutralization. I'll skip these slides for now. We'll go through next part. In section 4, we will go through neutralization. We will see how to write the chemical equation for neutralization reactions and how to explain the neutralization reactions that are used in acid-base hydration. The last objective of section 4 to compare the properties of buffered and unbuffered solutions. We will talk about indicators as well. So we have stoichiometry vocabulary that will be used in this section as well. Let's go back to section 3 for now and focus on the pH and pOH. What are both pH and what are pOH concepts? In this section, we will just revise what's the meaning of Le Chatelier's principle, which is about equilibrium. Le Chatelier states that if a stress is applied to a system at equilibrium, the system shifts in the direction that relieves the stress. So we are going to go to the side that is, I can say, have less stress. Okay, what are the new vocabulary? We have Kw, or what do we call it, ion product constant for water, and then we have pH and pOH concepts. What is pH of water? pH of water is what? pH of water means you have sorry. pH of water is the scale that we will describe here when we come to this slide, that describes how much of acidity or basicity we have in a substance. Okay, so back to Kw. So pH of water value is going to be 7. That is going to be green in some indicators like the universal indicator that we will see. The ones on the right are the base. The one on the left are the acidic ones that we will see in the coming part of the section. So what is Kw? Kw is the ion product constant for water. You remember that K equilibrium talks about the constant of equilibrium. Here we have ion product constant for water. This is why we call it Kw, because it talks about water. Pure water contains equal concentrations of H positive and OH negative. So the concentration of H positive equals to concentration of OH negative in water. This is why we call it neutral. And this is why we will see later on why the pH of water equals 7. The ion product constant of water, which is Kw, equals concentration of hydrogen ion multiplied by the concentration of hydroxide ion, concentration of H positive multiplied by concentration of OH negative, which is described in the self-ionization of water. It's found also in the chemical equation H2 plus H2 will produce H3O positive and OH negative. We said H3O positive is similar to H positive. Hydronium ion and hydroxide ion together will be the water. With pure water at the temperature of 298 Kelvin, which is 25 Celsius degrees, body concentration of H positive and OH negative are equal to 1 times 10 to the power negative 7 molar. In the value here, we see that there is number 7 somehow. This is, what do we call it? The concentration. So 1 times 10 to the power negative 7 molar, this is the concentration of both H positive and OH negative. So we can say that Kw will be, as per the equation we put here, concentration of H positive times the concentration of OH negative. So 1 times 1 times 10 to the power negative 7 times 10 to the power negative 7. It's going to be 1 times 10 to the power negative 14. So Kw of water equals 10 to the power negative 14 molar, of course. Kw and Le Chatelier's principle proves that concentration of H positive multiplied by concentration of OH negative must equal to 1 times 10 to the power negative 14 at the temperature of 25 Celsius degrees or 298 Kelvin. As the concentration of hydrogen increases, then you will have an OH negative must decrease. If you have the opposite, if the concentration of H positive decrease, this means that OH negative increase. So one of them increase, the other decrease. So we have a balanced value of Kw. Now I want you to bring your calculator. I'll give you some time. Prepare yourself. Bring a calculator, piece of paper, or a notebook, and come with me to these calculations. The first example. We will have 5 questions in this section. So the first question, H positive, how to calculate the concentration of H positive and the concentration of OH negative using Kw. We said before Kw equals both H positive times 10 times OH negative, or Kw is 10 to the power negative 14 for the water. Okay, let's see here. At 298 Kelvin, the concentration of hydrogen ion in a cup of coffee is 1 times 10 to the power negative 5 molar. How could we calculate now the concentration of OH negative? So the question wants you to calculate the concentration of OH negative in the cup of coffee. Then the second question, is the coffee acidic or basic or neutral? How could we know? This is what we will see depending on either the pH or the concentration of H positive and OH negative. The one that is more will decide whether we have acidic or basic. If they are equal, it will be neutral. Let's analyze the question. First step, if you have any type of these questions in acids and bases, you need to analyze the question, decide what's given and what is needed. Okay, in this question, you are given the concentration of H positive, and you know that Kw equals 1 times 10 to the power negative 14. You can use the ion product constant expression, which is, what do we call it, Kw, to solve the concentration of, or to calculate the concentration of OH negative, because H positive is greater than 1 times 10 to the power negative 7. So you can predict that the concentration of OH negative should be, of course, 1 times 10 to the power negative 7, which means you will have more of H positive. This is why we will consider this as acidic. Okay, as per the analytical information here, or how did we analyze the problem? H positive equals 1 times 10 to the power negative 5. Kw was 1 times 10 to the power negative 14. Rho H negative is unknown. So how could we do it? First step, you put Kw formula. Kw equals concentration of H positive times concentration of OH negative. If you want OH negative, then you do Kw divided by concentration of H positive, and this is going to be what? 1 times 10 to the power negative 14 over 1 times 10 to the power negative 5. The final answer is 10 to the power negative 9. We will know that as concentration of H positive was 10 to the power negative 5, which is more than 10 to the power negative 9, which is OH negative, then this coffee is acidic, and you will know from daily life examples that coffee is acidic. So this example was a good example of getting OH negative from the concentration of H positive. Let's move on now to pH and pOH concepts. The concentrations of H positive ions are often small numbers expressed in scientific notation. This is why we usually have, let's say, 5 times 10 to the power negative 9. Or we have 1 times 10 to the power negative 7, which is like the water example. What's the meaning of pH? And how could we use the concentration of H positive to get the pH scale or the pH value? pH, from the definition, is the negative logarithm of the hydrogen ion concentration of a solution. So, looking at its math, pH equals negative log of concentration of hydrogen ion. Sometimes you have hydronium ion. So, pH equals negative log or logarithm of concentration of hydrogen. If hydrogen ion concentration is given, then you can calculate pH using this formula. Very easy. You need to memorize this. You need to know how to use it to calculate pH. This is what we will see in the coming slides. So if we take this pH scale, okay, if we take this pH scale, looking at the scale on the right side, you have 0, 1, 2, 3 until you reach 14. Okay, examples are given from the bottom. Gastric acid, so because we start from 0 to 6, these are the acidic ones. Then we will have number 7 as neutral, which is distilled water, H2O only. From 8 till 14, it's going to be considered as basic. Okay, gastric acid, that is red at the bottom, pH equals 1, is the strongest acid we have in this scale. Then we have lemon. Okay, of course, as you go up, the acidity will decrease. As you go up, basicity increase. As you go down, go the opposite. If pH decrease, then you will have stronger acid or more acidity, and you will have less basicity. Of course, this is because acid and base are opposite to each other. Let's continue. Lemon juice is number 2, orange juice number 3, tomato juice number 4, black coffee is number 5. This is the one that we just talked about from previous example. Looking at black coffee, the value here is 5. Let's go back to previous example. Concentration of H positive was 10 to the power negative 5. This is how we got number 5, because the negative log of this concentration will give you number 5. Back to urine, this is number 6. Number 7 is neutral, which is distilled water. Then we will start with bases. Seawater, 8. 9 is baking soda. 10 is milk of magnesia. 11 is ammonia solution. 12 is soapy water, which is actually the soap itself. Bleach is number 13. Bleach is called also Clorox in the commercial names, or Hypex in Jordan. Okay, number 14 is like the extreme value of pH. I think we don't have exactly 14 and we don't have exactly 0. We have something like 13.9, for example, by calculations. We have like 0.1. but I never studied example with pH equals 14 exactly or 0 exactly. Fine. Let's see now the other indicator, or what do we call it, other graph diagram for pH. The scale here shows sorry, pH here shows you different values going from the top to the bottom. We start from 0 till 14. You see battery acid is 0, stomach acid is 2, lemon juice is more than 2, let's say like 2.4. We have soft drinks, which is the Pepsi, Cola, all these bad fizzy drinks, they are acidic. Okay, vinegar is like 3.5, tomato is about 4.5, coffee at 5, milk is around 6.5. You have pure water at number 7. Blood is around 7.4, 7.3. It depends on the reference you will use. Seawater is under 8. Antacid, which is the medicine like Gaviscon, for example, but it's not exactly Gaviscon. Gaviscon uses something else here between 9 and 10, which means antacid is pH equals 9.5. We have detergent at number 10, milk of magnesia at number 10.7, household ammonia is number 12. We have oven cleaner around 14. This is why it's very strong, because it can clean very hot places like the oven and remove all the grease from there. We have now another example on how to calculate the pH from the concentration value of hydrogen ion. So activity 2, what's the pH of a neutral solution at 298 Kelvin or 25 Celsius degrees temperature? How could we solve it? The first step, you will know what are the unknown. The unknown is pH. They want you to calculate pH, so you are going to use this equation, pH equals negative log the concentration of hydrogen ion. Then you will substitute the value of hydrogen ion using the concept you studied from KW. We knew that for water here, neutral solution like water, concentration of H positive equals 1 times 10 to the power negative 7. If you take the pH, which is the negative log of these, that will be negative log of 1 times 10 to the power negative 7 is going to be 7. So the pH of water or pH of any neutral solution will be 7. Is how we calculated the concentration of is how we calculate the pH from the concentration of hydrogen ion. So the known information was concentration of H positive, the unknown was pH. This is how we did it. What's the meaning of pH? From the name, pH looks for the concentration of hydrogen. So what is pOH? You are right. pOH looks at the concentration of hydroxide ion or OH negative. So pOH of a solution is the negative logarithm of the hydroxide ion concentration. pOH equals negative log of concentration of OH negative. pOH equals negative log of concentration of hydroxide ion. The sum of, okay, here is the a new equation we will use. The sum of pH and pOH equals 14. So if you see this scale, you will see that the concentration of pH and pOH are inverse. So if pH increase, pOH decrease. As you go to the right, go to the left, pOH increase, pH decrease. Okay, so increasing of acidity came by the decrease of pH or increase of pOH. What about the increasing of basicity? It's the opposite. As pH increase, then the basicity increase. As pOH decrease, then you will have more basicity. Neutral is number 7, which is the concentration of H positive equals 10 to the power negative 7, concentration of OH negative 10 to the power negative 7. Both pH and pOH are 7 at this point. Example of neutral is water, as we said. And it's not any water, it's H2O, the pure water, or distilled water. Okay, for all strong monoprotic acids, the concentration of the acid is the concentration of of H positive ions or hydrogen ion. So for strong monoprotic acids like HCl, the concentration of the acid is equal to the concentration of the H positive. The same will be for bases. The concentration of strong bases equals to the concentration of OH negative for the strong bases. And the concentration of these bases will be equal to the concentration of OH negative. So concentration of NaOH equals to the concentration of OH negative. Very simple and easy. What about the weak acids and bases? Weak acids and weak bases only partially ionize, and you have K and Kb values must be used. For litmus paper and a pH meter with electrodes, we can determine the pH of a solution. So depending on the pH values and depending on the pH meter that has electrodes, we can determine whether we have, for example, pH equals 7, 8, 9. So we have a meter for this scale, like we have a weighing balance, then we will have a pH meter. Okay, in the third activity here, we see that we have the concept of how to calculate pOH and pH from the concentration of OH negative. You remember, OH negative is related to pOH. So from pOH, we are going to calculate pH later. Let's see what do we have here. A cow is being fed straw and hay that has been treated with ammonia. The addition of ammonia to animal feed promotes protein growth in the animal. Another use of ammonia is as a household cleaner, which is an aqueous solution of ammonia gas. So remember, ammonia was basic. So here we talk about a high concentration of OH negative. A typical cleaner has a hydroxide ion concentration of 4 times 10 to the power negative 3. From this value, we are going to calculate both pH, pOH, and we can know all this from the given information. We have OH negative, we need to calculate pOH and pH. First of all, we should calculate pOH. From pOH, we will get the pH. How to solve this equation? You will use the concentration of OH negative to get pOH that equals to negative log of concentration of OH negative. So you are going to substitute the value of concentration of OH negative, which is 4 times 10 to the power negative 3 molar. pOH equals negative log of 4 times 10 to the power negative 3. Using your calculator, you are going to know that pOH equals 2.4. If pOH equals 2.4, I will go back with you to this sentence. We said the sum of pH and pOH equals 14. The sum of pH and pOH equals 14. So if you have pH plus pOH, they both will be 14 at any certain point from that scale. If pOH was 2.4, what do you think the value of pH? Let's see. We will use that relationship, pH plus pOH equals 14. And we will see that pH, if you take it on one side, keep it on one side, take the pOH on the other side, using the math skills, 14 minus pOH will be 14 minus 2.4. The value of pH equals 11.6. So this is going to be basic. pH equals 11.6, and we know that if you have pH more than 7, then you have basic. We said the value is around 11 point something. Go back to the value. It's around 11.6, so this is basic for sure and strong basic. So ammonia is basic. Sorry, it's not that strong. Okay, let's calculate the concentration of H positive and OH negative from a pH. So now we will go through the opposite. If you have pH, how could you calculate the concentration of H positive? And from the H positive, we will know later on how to calculate the concentration of OH negative using the KW values. Okay, let's read this. Activity 4. What are the concentration of H positive and OH negative in a healthy person's blood that has a pH of 7.4? Assume that the temperature of the blood is 298 Kelvin. So, knowing that the pH value is 7.4, you are going to calculate the concentration of H positive, and then from that value we will have the OH negative calculated as well. The known is pH only. We have to calculate the H positive and OH negative concentrations. Of course, mole per liter is molar if you still remember these concepts. Okay, how could you solve this? You're going to use pH equals negative log of H positive, and then we will say that we have, what do we call it, multiply both sides by -1 to cancel this negative. We will keep the H positive. You can either memorize this or, what do we call it, derive this. Okay, so we will have now log of concentration of H positive equals negative pH. So take the antilog of each side to solve the concentration of H positive. Concentration of H positive is going to be antilog of negative pH, and all this is going to be calculated now. Substitute pH equals 7.4. You will have the concentration of H positive will be antilog of negative 7.4. Using your calculator, you will know that it's going to be 4 times 10 to the power negative 8. So concentration of hydrogen ion will be 4 times 10 to the power negative 8. If we know this, we are going to use our KW concept, or this other way, which is pH plus pOH will give you 14, and then we will get pOH. From the pOH you will know the concentration of OH negative. There is another way. We will say that the concentration of H positive multiplied by concentration of OH negative will be equal to 10 to the power negative 14. If you get that, you will know that later on that OH negative will be 2.5 times 10 to the power negative 7. If you have both these two values multiplied by each other, you will have 10 to the power negative 14. If you keep H positive 4 times 10 to the power negative 8 and OH negative 2.5 times 10 to the power negative 7, then you will know that the KW is 10 to the power negative 14, or 1 times 10 to the power negative 14 for any acidic basic solution. Okay, good practice so far. The last question about the Ka, Kb, and the pH values. Here you are going to use the Ka of Kb or the pH. We will have a relationship now between the pH value and the Ka. We will see. Activity 5. Formic acid is used to process latex tapped from rubber trees into natural rubber. The pH of this was 0.1 molar solution of formic acid. The formic acid is HCOOH. This formic acid came from ants, by the way, if you don't know. So formic acid has pH of 2.38. the concentration of this acid was given 0.1. Do we think that this is a strong or weak acid? We will see. If you see pH equals 2.38, the concentration of a solution given also 0.1, the Ka is unknown. Let's use our given information. pH equals negative log concentration of H positive. We need to calculate now the concentration of H positive. You know how to get it from previous question. So concentration of H positive will be negative, antilog of negative 2.38. By getting the calculations, H positive will be 4.2 times 10 to the power negative 3 molar. This is also equal to the concentration of the acid because this is a strong acid. How did I know it's a strong acid? Go back to previous part. You see that pH equals to 2.38. And this is very near to 0 compared to the 7 value, which is a neutral. So going back to the question, the concentration of acid, which is HCOOH, equals in the initial concentration of H positive, which is sorry, I made a mistake. This is weak acid because we have Ka value. Yeah, sorry for that. So here we have this concentration of acid minus 4.2 times 10 to the power negative 3, which is the concentration of H positive. Because going back to Ka values, we know that, or if you want to write the ionization equation or the chemical reaction that happened, chemical equation will show you that the concentration of H positive multiplied by concentration of HCOO negative will be on the products, and the concentration of HCOOH, which is the acid, will be on the other side, and the water, because water is not considered in the K or K equilibrium of Ka values. Then we will have only 3 parts. The concentration of H positive was given, the concentration of the acid will be calculated as 0.1 minus 4.2 times 10 to the power negative 3. This is going to be 0.096 molar, and getting the value of Ka will be by having this equation. Ka equals concentration of H positive times concentration of the ion, okay, the negative ion, over the concentration of the acid. So we already have both the acid and its ions. Concentration of H positive equal to the concentration of the negative one, HCOO negative, because they both will be ionized equally. Okay, so we still have the concentration of the weak acid. Sorry, I cannot say strong. Okay, so the concentration of this acid equal to 0.096. So by getting the calculations, you will have Ka equals 1.8 times 10 to the power negative 4. So the acid ionization constant for HCOOH, or this acid, is going to have Ka equal to 1.8 times 10 to the power negative 4. Okay, back to the section. Let's go back and revise. What did we cover so far? We had the concept of Kw. We had Kw equals concentration of H positive times concentration of H negative. We knew that the Kw should be 10 to the power negative 14. We should use calculators to get the concentration of OH negative if we have H positive, or if we have OH negative we will get H positive, and so on. So if we have one of these H positive and OH negative, we can calculate the other one. like this question here, because Kw is 10 to the power negative 14, so it's gonna be straight away. So pH and pOH, they both talk about the concentration of either H positive or OH negative, depending on the scale. pH talks about concentration of H positive, pOH talks about the concentration of OH negative or hydroxide. You need to know some examples of acids and bases, like the values of pH, for example, for distilled water, for bleach, for gastric acid. These are important. I can say that these are the terminals or the edges and the common examples. In this example here, the activity, we calculated the pH from the concentration of H positive, which is a direct question. Just get the negative log of that concentration. If you have the pOH, you can get it from the same way. The pOH will be sometimes getting the OH negative to calculate the pOH. From the pOH, you can get the pH by getting the pH plus pOH equals 14. This is the direct way to calculate the pH if you have pOH. And next we had activity 4 that talked about how to calculate the concentration of hydrogen ion and hydroxide ion if you have a given value of pH. So you are going to do the antilog here, and you will follow these steps as we did before. If you have Ka and pH, the relationship between them, you need to go back to the concentration of H positive. So if pH is given, you will get the concentration of H positive. From concentration of H positive, you will have also concentration of the whole solution. You have the concept of getting Ka by dividing the product's concentration over the reactant's concentration, which is the K equilibrium concept. Ka was getting or coming from the concentration of acid and the concentration of H positive. So all these are given and calculated. So Ka value was calculated at the end of this question. So back to this. Now we have some questions to check your understanding. In dilute aqueous solution, as the concentration of H positive increases, if concentration of H positive increases, what will happen to pH or pOH or OH negative? Let's see. You will think about it correctly, so you will get all of them above. So if H positive increase, then pH decrease, you will have more acidity. Then pOH will increase if pH decrease, because these are inverse to each other. The concentration of OH negative will decrease. Okay, and that's it. What's the pH of a neutral solution? What is the pH of a neutral solution? Of course, it's 7, like the pure water. That's it for now about section 3. Let's move on now to section 4. Section 4 talks about neutralization. Neutralization is using stoichiometry, is using some calculations, the quantitative relationship between the amounts of reactants used and the product formed by a chemical reaction. So we are going to use the law of conservation of mass here. We will use some concepts of getting the calculation of how much of acid is going to be added to, let's say, X value of base. In acid-base neutralization, usually we have some calculations. If we don't have, it depends on your textbook. If you don't have these, you just need to memorize the main concepts. The main idea is, in a neutralization reaction, an acid reacts with a base to produce salt and water. New vocabulary is given here. You have neutralization reaction, salt, titration, titrant, equivalence point. We have endpoint also,
Acid-base indicator, salt hydrolysis. Salt hydrolysis is not considered as a part as part of your lessons if you study some of the textbooks. So sometimes you don't have salt hydrolysis, sometimes you don't have buffer, or it's cancelled from your curriculum. You need to check with your teacher. You have buffer and buffer capacity. This also talks about solutions that are part of acid and base chapter. These antacid tablets, we use them to treat the heartburn, or if you eat, for example, a lot of acidic food, or for example, for eating the fast food, some doctors advise you to use antacid to neutralize your pH of the stomach. Why? The reason? Because these antacids are bases. These are actually bases. Sometimes you have high acidity in your stomach. People may use their natural way. They will eat a cucumber, or they will tell you to drink a lot of water. Some people they eat cucumber. So it depends. You eat cucumber, you eat an apple, you do whatever our grandparents did before. Some people they like to use the medicines. It's either to use antacid, or some people they use Gaviscon. All these are examples of neutralization, because if the acid is high, we want to decrease this acid or increase the basicity. I'll give you some time to look at these substances in this reaction, HCl and NaOH. What will happen if you add them together? Back to the explanation. HCl plus NaOH is a neutralization, a very common neutralization reaction. This will produce water and salt, water and NaCl. From where did we get NaCl? Because it's a double replacement reaction. You will have H going to the OH and the Na going to the Cl, so you will have NaCl and H2O as the product. What kind of solution is produced when these reactants react in stoichiometric quantities? The solution produced, we will call it salt and water. Explain why do we call this reaction with this name, which is neutralization. Use scientific reasons or reasoning describing the reaction. Because we have an acid HCl and a base NaOH, we are going to have, this is if we take pH equals 1, this pH equals 13. If you add them together, it's 14. Split the 14 into 2, you will have 7 and 7. This is the basic concept, came from neutralization. You will add an acid to a base, but you don't actually add the pH. We will see later on how to get it. So neutralization reaction, okay, it came from mixing acid to base and will produce water and salt, which are both neutral. We call it neutralization reaction because the pH of acid and base solutions of the reactants will be neutralized or neutral in the products that are water and salt. What is neutralization? From whatever we just discussed, it's a reaction in which an acid and base in an aqueous solution react to produce a salt and water. The salt is an ionic compound. It's made up of cation and anion. The cation is coming from the base and the anion came from acid. Example of that, if we look at there, NaCl came from the Na, the cation came from the base, NaOH, and the Cl, which is the negative ion, what do we call it? Anion came from the acid. If you go back to this, think about it, you already applied whatever we discussed about the salt. Under which type of reactions do we classify neutralization? Is it synthesis, combustion, decomposition, single displacement, or double displacement? Of course, we will choose the double displacement, or what do we call it, double replacement. Okay, if we take water, two water molecules will be coming from H3O positive and OH negative, or the opposite thing. If you have an acid and a base, HCl plus KOH, you have dissociation of these ions, and then you are going to have the H and OH will be together, and the K and Cl will be together to produce KCl, and this is called dissociation happens if you have HCl and KOH because they both dissolve in water or the aqueous solutions. We are going to have dissociation of these ions. So we had cations and anions that will be attached together to give you water, and KCl, which is the salt. The salt is ionic compound. The ionic equation is explained here, and the ionization that occurs in a neutralization reaction came from the concept of having cations and ions, or both sides of the ionic compound will be a cation and an ion when dissolved in water. What's the meaning of titration? Think about the titration. Titration is, what do we see in this picture? If you add a base to an acid with quantitative values, or the opposite, sometimes we add the acid to the base. It depends on your reaction or the process, what do you want to do. Titration is a method for determining to determine the concentration of a solution. So we are going to determine or calculate the concentration of a solution by reacting a known volume of a known concentration of that solution with a known concentration of a known solution. For example, let's say here, I don't know how much of acid is found there, but I will know the volume. So I don't know the concentration of that acid, but I know its volume. I know the volume that will be added. I know the concentration of that base. So the solution that I know its concentration will be in the burette, and the concentration that is unknown that we need to calculate will be in this flask. Simple and easy. If you know the concentration, you keep it in the burette. If you don't know it, you keep it in the flask. You have a stopcock here, or what do we call it? Let's call it a stopper, for example, if you don't know what's stopcock. So you're going to use this to control how much of the known concentration to be added to the unknown concentration by using some calculations, CV and CV, which means you are going to know the number of moles used in both that will be equal to each other. By knowing this, you will calculate the molarity, or what do we call it, the concentration of that unknown. So what are the steps of titration? In a titration procedure, a measured volume of an acid or base of unknown concentration is placed in a beaker. We said the unknown will be in the beaker at the bottom, and initial pH recorded. We need to have the value of pH. By knowing the value of pH, you will know the concentration of H positive or OH negative, whatever you want to use for later on. The burette is going to be, burette is this. Okay, if you don't know what's burette, burette is filled with the titration solution of the known concentration, as we said. If you know the concentration of a substance, we will call it titrant. Okay, next, measured volumes of standard solution are added slowly and mixed into the solution in the beaker, and the pH is read and recorded after each addition. So after each addition, let's say after we add each 5 milliliters or 2 milliliters, we are going to calculate the pH or read the pH, sorry. From that, we are going then draw a diagram like this that we will see later. The fourth step, the process continues until the reaction reaches the equivalence point. Equivalence point is the point at which number of moles of hydrogen ion will be from the acid will be equal to the number of moles of OH negative ions from the base. So equivalence point has number of moles of hydrogen ion will be number equal to the number of moles of hydroxide ion. The titration process can be done using this holder, okay. To fill the acidic solution or the basic solution, you need, what do we call it, a pipette. This is the most accurate tool we use in the chemistry labs to get the volume with no mistakes. We usually avoid the mistakes by using pipettes. So if you want 10 milliliters, you will get exactly 10 milliliters. No mistakes, nothing will be lost. Here we have 20 milliliters of acid solution. We get it from this tool. The initial volume reading is going to be at the top. The burette is this glassware, and we have standard NaOH solution. NaOH is the base here. We have here the acid solution. If you see, we don't have any colors, means the both are colorless. They used here a blue color just to show you that they both are colorless, like made up of water, okay? We had known, careful, you have known, you know what is the concentration of NaOH, you know how much of volume you will be added, because you will calculate how much did you add, okay? How much did you add is going to be equal to the final minus the initial, final minus initial, or initial minus final. This is how much you added from that NaOH. The solution of acid has 20 milliliter, which means you know the volume but you don't know the concentration. After a while you will have whatever you added from the base will be added also to the volume of acid. So the total here and the total in the burette will be the same. If you have total here, let's say total here was 50 plus 50, 100. Here you will have total of 100 if you add whatever remain in the burette and whatever you have in the flask. After you have the neutralization happened, you had here a change in color. It shows you that the acid is not acid anymore, it's going to be base, or it's going to be something else, maybe neutral, we will see. So neutralization solution or neutralized solution, we are going to add indicator here to show you that whether you have reached that equivalent point. Titration of an acid with a base, sometimes we use phenolphthalein as indicator. Phenolphthalein is pink for the basic and colorless for the acid. This is an acid, colorless. You see, once you add in figure 1, you have a starting point. Slow down because you started seeing this, let's say after 5 minutes of adding 20 milliliters of NaOH, you had this pink color shown here. So slow down now, drop by drop, and then swirl, or what do we call it, mix it well until you reach the end point. At the end point you will have a very faint or light color of that indicator, and then if you go too far we will call it now a new solution. Now if that one was acidic, it's not going to be acidic, the pH has been changed. So you have indicator shows you that you have basic now, yeah. So whatever you have in the flask has been changed. What is the end point? Before the end point you have no color. At that end point you add faint color overshot, or if you add a lot of base to the acid, it will be the dark color or past the endpoint. Indicator used here, we use phenolphthalein. How did I know? Because it's pink in the basic solution and it's colorless in the acid. This is what we will see in the coming this slide. Let me show you this slide. We will see that phenolphthalein here, if you have acidic or basic, is going to be shown what type of solutions. Back to titration process. If you have titration, you need to know how could you measure, how could you see how much of base is remaining here. So you look at the burette from the same level of your eye. The bottom of that water drop will be coming like a curve down. So you look at the bottom. You don't look at the top because this is made up of water. It comes like this. Okay, curve goes down. This is 27.76 because it comes between, okay, it comes from 0 until 28. It's coming before 28 because it's here between 27 and 28. You have 1, 2, 3, 4, 5, 6, 7, and something else. So 7.7, almost 7.6. So move your eyes to the level of the liquid surface and read the value of the bottom of the meniscus. This is called meniscus, with 1/10 of the smallest scales. These are 1 to 10 scaled from 0 to 10. We have 10 dots. Okay, actually 9. Okay. So the smallest scale marked on the burette was here. You start from this until you reach here. You see how much did you read. Swirl the flask continuously until one drop of the titrant causes a color change to remain. A white sheet of paper can be placed, so you can put sometimes a white paper below this flask so you can see that it's white or colorless or pink or whatever. Okay, so you can see this color clearly. Then you can determine the endpoint. This diagram here shows you adding 50 milliliter of 0.1 molar of HCOH acid that is titrated with 0.1 molar of NaOH. So you have acid is added to a base here. So how much of NaOH was added? If you added, let's say 47 here, 47, yes, you will have equivalence point. Okay, watch this. Phenolphthalein, so you are going to talk about pink in the basic. You're going to see colorless for the acid. The volume added, if you start from 0, so you added NaOH to the acid, HCOOH. You have some information mentioned in this, and you have NaOH also added to another type of acids that is strong. Here is strong acid, here is weak acid. This is why you don't have a sharp equivalence point. Here you have a sharp equivalence point. You can see that it's sharp because there is a jump from 40, let's say, until 50. There is a jump from 2 pH equals 2 until you reach 11 point something. Previous one, from 40 you had 5.7, for example. You reached up to 12 here by the 50 milliliters. So the change or the drops that been added from NaOH was effectively giving you the clear sharp change, and the equivalence point was clear between 40 to 50 milliliters of, and that exactly came from 47 milliliter of NaOH when added to 50 milliliter of 0.1 molar of HCl. The indicator used here was called bromthymol blue. Sorry for this. I never use it in the lab. So yeah, we have bromthymol blue. You don't need to memorize them. If you consider now a base added to an acid, here is weak acid, strong acid, strong base. So if you add a strong acid to strong base or strong base to a strong acid, you will have a sharp titration curve. We call this titration curve. And you have a small change or slight change. You can mainly you can see the equivalence point, but it happens directly and very quick. Change of the pH values came from between 45 till 47 milliliters of NaOH added. Here we see that we have the opposite. If you add HCl to NaOH, you're going to have pH is very high. For NaOH was 13 until you reach the value of 1 pH for HCl. If you added all the HCl to the NaOH, so you will have more acidic now. If you have the normal way, we add NaOH to the HCl, you have HCl pH equals 1, you will have increase of the pH until you reach the equivalence point, the pH equals 7, then it will reach until 11, 12 point something, then it will be about 13 when you add all the NaOH. Use your calculator now to help me with getting these values. Now we are going to calculate the molarity of an acid using what? We are going to see that the 18.28 milliliter of the NaOH is given. So you have volume of NaOH, you have concentration of NaOH, and we have 25 ml. So we only know the volume of that acid, but we don't know its molarity, so we need to calculate its molarity. So volume of acid is given, but molarity or concentration of acid not given. We need to calculate it. Molarity and volume of the base are given, V of base and M of base. They both are given. In this example, we are going to say that you need to write the chemical equation that is balanced. HCOH plus NaOH will give you HCONA plus H2O. You need to know how to make the double replacement, so you will get H from here going to other OH to give you this H2O, or you take this H from this side. Whatever you do is just need one H from this HCOH, give it to OH and take that Na to replace it for the acid. So write the acid to base mole relationship. We can see that we have 1 to 1 after balancing the equation, which means the number the numbers that we will use here will not be changed. We don't have any ratio. Okay, convert the volume of the base from milliliter to liter. We should use everything here in liter because the concentration will be in mole per liter. So volume of base was 18.28. We are going to convert it, will be 0.01828 liter. The same will be for the acid. We are going to make it in liter. That is whatever we will use also for later on. Okay, so apply the relationship between the moles and the molarity. You know this from previous chapters. Mole of NaOH equals CV, or molarity times volume. So
the number of moles of NaOH, we need to calculate it. We get that from doing multiplication from the molarity or the concentration of that base by its volume. We use whatever is given in the question, do calculations. You will have 1.828 times 10 to the power negative 3 mole of NaOH. Then you need to calculate the number of moles for the acid. It's gonna be the same because the ratio is 1 to 1. Okay, so next step will be apply the relationship between moles of acids and molarity of acid and the volume of the acid. We will use now, what do we have about the acid? We have the concentration not given, we have volume, and we have moles. If the moles are given now, the volume is given, we can calculate the concentration by dividing the moles over the volume. Volume was 0.025 liters. So just do calculations. The molarity or the concentration of that acid was 0.073 molar. That's it, very easy and simple. You just need to get the number of moles. And if you have a mistake in this chemical equation that is not balanced, or you don't know how to deal with the ratios, if you have ratios, then you need to revise this example again and again. You have a lot of examples in your textbook that you can practice on. Indicators. Chemical dyes whose color are affected by acidic and basic solutions are called acid-base indicators. What is the end point? It's the point at which the indicator used in titration change its color. The indicator will change the color at the equivalence point, not the end point. The end point comes after the equivalence point, usually. Equivalence point is when you have the concentration equal to each other. The end point is where do you see the change of the color. When you see the change in the color, this means that you already passed the equivalence point. Okay, we see here some indicators. You don't need to memorize anything. Just need to know bromo, phenol, blue, methyl orange or methyl orange, methyl red. Sometimes we use it. Sometimes we used this bromethymol blue. It depends if you have it in the schools or universities. It's common one, but not everywhere used. Okay, phenolphthalein, phenol red. We have a lot of examples, but the universal indicator is the most common one. We use it actually to know the value of pH instead of getting the pH meter. So if pH equals 5, 6, 7, 8 until 13, you will know from the scale here what's the value of that pH. Okay, salt hydrolysis. In salt hydrolysis, the anions of the dissociated salt accept hydrogen ions from water, or the cations of dissociated salt donate hydrogen ions to water. So, salts that produce basic solutions. We have also salts that produce acidic solutions, and we have salts that produce neutral solutions. Let's have a look on each. If Kf is the salt of a strong base, it came from KOH, then the weak acid is HF. Looking at Kf, it came from K positive and F negative. K came from KOH, which is the base, while F came from weak acid, which is HF. So this salt will be called basic because it came from stronger base or strong base. So Kf is considered as strong base because it came from strong base. Sorry, it's called basic salt. Okay, so it's basic salt or basic solution. Type, if we dissolve NH4Cl in water, it will be acidic. So it's called salt that produce acidic solution. NH4Cl is the salt of a weak acid. Weak base is NH3. We know ammonia is weak base.
the strong acid is HCl. So Cl came from a strong acid. This is why it's going to be affected the water or the solution to be acidic. When dissolved in water, the salt dissociates into ammonium ions and the chloride ions. If you dissolve it in water, it will give you NH4 positive and Cl negative. Easy and simple. The last one, if you have NaNO3, sodium nitrate is the salt of a strong acid HNO3 and a strong base NaOH. If you have strong acid and strong base, you're going to have a neutral solution. Example, NaCl. It came from NaOH and HCl. So little or no salt hydrolysis occurs because neither Na positive nor NO3 negative react with water. What are the buffer solutions? This is the last part of this section. The pH of blood must be kept within a narrow range. So buffers are solutions that resist the change of pH when limited amounts of acid or base are added. So buffers are the solutions that resist the change of pH. For example, our blood. If you have acidic blood, you will die. If you have basic blood, too much basic, you will die. So we have something around 7.4, 7.3, let's say around 7.2. If we eat something that decreases the blood level, or we have a lot of shortage in oxygen, and something happened to our body, that pH of the blood was affected, then we need to take the concentration of that. Our blood is a buffer. Okay, so a buffer is a solution made up of a weak species and its conjugate. So our body had a lot of buffers. This is why in the past, when they studied buffer, they considered that as part of human body. A buffer is a solution made up of a weak species and its conjugate. We will see like a weak acid and a strong salt and base and so on. Ions and molecules in a buffer solution resist a change in pH by reacting with any hydrogen ions or hydroxide ions added to the buffer solution. We have HF that produces H positive and F negative. When acid is added, the equilibrium shifts to the left. So if we have acid added, so we are going to be going to the acidic side, HF. Additional H positive ions react with F negative ions to form undissociated HF molecules, but the pH change little bit. So what is the meaning of buffer capacity now? It's the amount of acid or base that a buffer solution can absorb without a significant change in pH, that we will call it buffer capacity. We have some examples of buffer solutions, giving you the buffer pH. For example, HF and F negative. So HF is the acid and its conjugate base. CH3COOH is the acid and its conjugate base. We have NH4 positive and NH3. NH4 positive is the acidic part. So I'm going to say that NH3 is base and NH4 positive is the conjugate acid of that. You see the buffer pH is different. For HF you have, because it's acidic, the buffer pH is around 3.2. CH3COOH is acetic acid or vinegar, and that one has a buffer of 4.76 pH. Let's take NH3 because it's basic. The value of pH was 9.4. What are buffer solutions? Buffer solutions most effective when the concentrations of the conjugate acid base pair are equal or nearly equal. So we see here some buffer equilibrium, that equations, and then that's it. So we said buffer pH are different depending on the conjugate acid and base. So if this is basic and you have its conjugate acid, you are going to have a buffer pH coming with the basic range. If you have a basic solution and its conjugate base pair, you are going to talk about the pH in the acidic range. Let's check our understanding. In neutralization reaction, and acid and base react to form salt and water. That's easy. Solutions that resist the change of pH, we call them buffers. Direct question. We have a summary here. The concentrations of hydrogen ions and hydroxide ions determine whether an aqueous solution is acidic, basic, or neutral. The Arrhenius acid must contain an ionizable hydrogen atom. An Arrhenius base must contain an ionizable hydroxide group. The Bronsted-Lowry acid is a hydrogen ion donor, while the base one is the hydrogen ion acceptor. The Lewis acid accepts electron pair, while the base donates the electron pair. You have a lot of concepts here that we covered, like Kw equals the H positive times OH negative, which is the ion product constant. It's going to be 10 to the power negative 14 for water. And pH of water equals 7 because the concentration of H positive is 10 to the power negative 7. pH equals negative log of H positive. pOH equals negative log of concentration of OH negative. pH plus pOH equals 14. We already studied all that. And you have now quiz time. Quiz time. What's the conjugate? We have 10 questions now. Focus and try to solve them without my help. What's the conjugate of a weak acid? Weak acid. What is the opposite of weak acid? It's strong base. Correct. Which type of acid accepts an electron pair? The acid that accepts electron pair. Electron pair. This is Lewis. Correct. In a solution where the pH equals 4, what's true about this? If pH is 4, this is more acidic. So acidic means we have higher concentration of H positive. The answer is A, correct. Salt hydrolysis, in which type of reaction? This is the decomposition, because if you go back to salt hydrolysis, let's go back to salt hydrolysis. This is the salt hydrolysis. You just need to break down the salt and see what will happen to that salt, whether it's coming from a salt basic or acidic solution. Okay, we are in question 5. The strength of a weak acid is measured by strength of a weak acid. How do we know that we have a weak acid? It's K. So K is acid ionization constant, correct. What's the pH of 0.25 molar of HBr? This is a strong acid. What do you think the value of pH by calculation? The pH will be 13.2 because it has a very low, which is 0.8 pH. Here they ask you about pOH. Be careful. If you have a question about acid, maybe they will ask you about pOH. It's not direct question the whole time. Which of the following is a diprotic acid? Diprotic acid. Di means 2, so H2SO4. This is mono. This is mono. This is not an acid actually. This is a base, an H3. I don't know why they put here the plus. They try just to make you confused. What's the conjugate acid of the following equation? You have HCl, H2O will produce H3O positive and Cl negative. Conjugate acid. This is acid. So not this one. This is base, not this one. What is coming with the base? Yes, conjugate acid is H3O positive. Correct. A decrease in concentration of hydrogen ions when hydroxide ions are added to an aqueous solution is example of Le Chatelier. Here we talk about equivalence.
Which of the following is a polar molecule? Polar. Okay. CH4 is non-polar. H2O, H2, PCl5. The answer is H2O. Water is polar. Thank you. If you have any questions, contact me or send me these questions in the comments. That's all about acids and bases. We are done with 2 lectures. I know this lecture was so long. I know we covered 2 sections and that was tough for you. You can have rest now and do the chapter test. Make sure that you understood everything. Good luck. I wish you all the best. My name is Mr. Qataiba. I will teach you also the other chapters of chemistry if you still need more help. Thank you.